Galina, I don't know if you have slides specifically for today that you're also sharing, but if you do, well, presumably those will all get put in the same place and where there's all the OMFIT tutorials. So welcome everybody. So yeah, I hope a lot of you saw Galina's talk on Monday. I actually had to miss most of it, but I've gone through the slides. So you guys have been making fantastic progress to getting OMFIT up to speed to use for NSTXU workflow stuff. So this is really exciting to see. And I know you got a lot of people that would like to take advantage of this. So I believe the intention today is for Galina to just go through and walk us through a tutorial example of running through a workflow usage of OMFIT for NSTXU, correct? So I don't yeah, so we're going to record this. I don't know if I need to say anything else or if you guys have anything else you want to say at the beginning. Otherwise, Galina, if you want to share your slides and get started, that's or however you want to do this, share your screen.
Yes, I will share my screen. I don't have the specific slides for today. Yeah.
But I assume, sorry to interrupt, I assume the point is if people have questions or if anybody's going to try to follow along and do this, that it's okay to, as long as we don't take 3 hours. If people have some quick clarification questions, we can go ahead and do that during the tutorial, correct?
Yes, we are happy to answer any short questions, and we are happy to set up another time if someone interested in more deep discussion for some particular aspects.
All right.
I would like to encourage people to, I think it's best to mostly watch along, because if you try and do it at the same time, you might miss some things. And this is going to be on YouTube, so we can have follow-up chats later.
Okay, sounds good.
Okay, great. We will start just from starting the OMFIT session on portal machine. To do it, you just need to type the model load mod OMFIT, when model load OMFIT. And usually I use the unstable as it's a recent version, and sometimes it might have some new updates compared to the just master OMFIT version. When we just start the OMFIT, it will load all Python environment what is necessary. So any OMFIT session will start from this window, and we have button continue to OMFIT. Today we are talking about the kineticEFITtime module. That's why we need to load kineticEFITtime. And before starting with kinetic equilibrium reconstruction, I want to load another module, what we call scope, just to see the basic parameters of the shot, what we will talk today about. So if we start with the scope module, we need to set up the shot number. Today we are talking about this shot. It is not NSTXU, it's just the NSTX shot with all available diagnostics. And during the shot, people observed the H transition. That's why it's a good choice to demonstrate the kineticEFIT tools. I would like to see some of the main parameters, like the alpha signal, like plasma current, injected power, neutrons, average neutron density, and maybe the storage energy. And I know what we shot was about 1 millisecond. That's why I can set the time range and plot all the signals. So we can see all the signals, and it gives us the brief understanding what was going on. So during this tutorial, we will look.
Can I ask a quick question?
Yes, sure.
It looks like you're loading these signals from EFIT 01 over on the upper right in the green there. Some of them at least, like the stored energy perhaps. So you already have, the magnetic EFIT, that was run for NSTX.
Yes.
And are you going to compare what you do with your kinetic EFIT to the, this is the magnetic EFIT 01, but there's also kinetic EFITs already existing for NSTX.
Yes, but the kinetic EFIT existing for NSTX doesn't have the contribution from fast ions. That's why we will make kind of the new one. And here, yes, I load the existing signals, kind of just to understand when the neutral beam injection started, kind of when we got the plateau phase for current, maybe if we had some huge ELMs or spikes in the alpha signals. I'm not going to
just sorry to interrupt. I'm just curious if that's where you're going at the end. Are you going to compare what you get to what already exists?
Not directly.
Okay, well, we could do that at some point.
Yes. Okay, today I wanted to look for this shot on times started from around 100 milliseconds to around 500 milliseconds. And to do this, we will load the kineticEFITtime module. We set our shot number here. And we can, starting from the EFIT 01 tree, and see the valid times for key files. Usually I just copy times from here. And paste it in this window. And since it will take some time to load all of these times, we will consider just only a few of them. So we will load only each tenth. When we fetch input key files.
Hey, Galina, is there, I mean, this is a tedious detail. Is there a way to just, without having to select, write down all the specific times, to just say, take all the files within a certain range? Like from 100 to 500, just whatever slices are available, just use those, or do you have to explicitly always write them out?
I'm afraid for NSTX, you need to specifically set up the times, otherwise you will get the kind of message what the times are not available.
Okay, thanks.
But if you know the interval between kind of recorded key files, you can just write it like the range between this value and this value with interval of 10 milliseconds, as it's a Python script.
Yeah, and if I may add, we're working on being able to generate our own K files starting from scratch, but that's something that is right now only available for NSTXU shots. And right now, it's we only can manage the magnetics, and we're working to add MSC and other constraints. So it's coming, but for now, I think this is the kind of the most tested and trusted way.
Okay, thanks.
Right. And some additional information on this step, kind of OMFIT, it's a tool what we constantly develop and making better. I shown you how to load the stable kind of common version. Right now, I will switch to another window where I have updated OMFIT version what I worked yesterday, because we found some points where we made the plots a bit better. Right now we are working in this window, and we continue just where we finished. We just loaded the key files, and now we go to the profiles tab. Because we want to start the first equilibrium with MSC data, and we want to start the first equilibrium with MSC data with correction for electric field. For this reason, we need to load the Cheers data, fit the plasma rotation to calculate the correction for MSC data and use it for EFIT afterwards. So we fetch and map all data. When we go to the slice tab, we can change the averaging window. We can change the window function. Or usually it works fine with default settings. If we set the two-shot interval for averaging window, we will get the warning message regarding the required parameters according to the time resolution of different diagnostics. So 20 milliseconds should be a good interval. When we slice all data, and on this step, it's possible to apply the symmetrization, what we were talking on Monday, to align the high field side and low field side Thomson scattering profiles, but we don't need it right now. When we go to the select tab and look on the spectroscopy diagnostic data, because we are going to feed the plasma rotation. So we're going to the omega toroidal, and we can see what maybe we don't want to include these channels. However, all of them are in the soul region, what we don't use in the analysis. Usually we look just up to the separatrix, but we can remove this channel. By clicking on the plot, we can see the number, and when we choose the right subsystem, and just deselect this channel, and it should be shown in gray color. Okay, we even don't see it because we limited our range only for selected channels. So everything should be fine with fitting. And then we can also check the MSC channels. We plot the slice data and we see some channels with a huge error. I know what this is, channel 17. So I also want to deselect it here. I also know what the channel 60 and 15 also have a huge error. That's why I will deselect them as well. And if we change the Y scale, we can see what the rest can be used for the analysis.
Can I make a comment again?
Yeah, sure.
So I don't want to start a whole thing, a whole discussion here, but people will know that this is a topic that comes up all the time in equilibrium reconstruction. You're giving people the power to toss out any data that they don't like.
Yes.
So which is, you know, it's a philosophy, which some people don't like. But just I think that everyone needs to be aware that if someone generates a reconstruction in this way, you don't necessarily know what they've done to the data. Correct?
Right. And we hope what kind of users they care about it before and they have a discussion with diagnosticians about kind of data. But this is a kind of preliminary preview.
So sorry, I probably shouldn't have started that because that is a whole topic, and I know that we've talked about it before, but just to make that point, that's all.
Yes.
I like the idea of starting another meeting, and it's well outside just OMFIT. It's this is scientific process, right? Because our field is standing on a lot of complexity, and this is true for just about anything, right? There's no way you could take a person's paper and reproduce what they did at this point. I like the idea of expanding discussion.
And again, not to get too far with this, which is maybe fine, you know, to give people the power to do that and to you know, play around with things or whatever, but as long as everyone's aware that this is what the situation is, and if your intention is to, you know, have each individual person be able to do what they want to make a reconstruction, then that's fine. If the intention is that, you know, this is a process and all these equilibrium reconstructions get written somewhere and other people use them, people need to just be aware that it's not a standardized process if you allow people to have control and throw out data they don't like. That's all.
Thank you. Yeah, it is right. Kind of here, we just demonstrate the tools, kind of what can be used. We not force anyone to do it, and we don't automatically write the results to the MDS Plus server or any public place. That's why, yes, of course, it's a responsibility of each user to decide if they trust to this equilibrium or not.
Yep, that sounds good.
Okay, when we deselected some channels, if we want or need, we go to the fitting tab. Okay, they're here, and we need to fit the omega. Right now, we fit it with the radial basis functions. We click the button fit and plot 1D. So, and we can see results for each time slice. To move to another time slice, I press the right arrow key on my keyboard, and we can see fitting for different times. So, and this fitting method usually is the fastest one and quite robust to fit the experimental points. When we need to calculate the post-fit quantities, and usually we set the poloidal rotation equal to 0 for NSTX. So now we have the all quantities what we need to calculate the electric field correction for MSC measurements. So we update profiles for iteration 0. And so now we are able to get this data through another module through EFIT.
Maybe, Galina, can I ask you to show people where the data is in the OMFIT tree? Under just to orient people.
Yes, when we worked with OMFIT profiles, we store all outputs here. We can have the raw data, we can have slice data, feed, derived quantities, everything what we calculated. When we updated OMFIT files for iteration 1, we have output kind of in the parent kineticEFITtime module. Here on iteration 0, we have the profile module and all outputs now here. When we finish equilibrium, we will have the equilibrium in the same place. So now we need to add the MSC data into EFIT module. We update data from OMFIT profiles. And it updated weight for all channels as I selected in OMFIT profile module. So you can see the weight equal 1 to all channels, except the 3 channels what I deselected from our analysis. It's also easy to kind of put them back and change the weight here. When we also add the correction, and it will set the electric field correction for all MSC measurements. And we have the isothermal constraints, where we set constraints based on the temperature at the separatrix. Usually I set the 60 EV. And we need to select the number of channels. Kind of ideally, we should use all 30 channels of Thomson scattering diagnostics, but sometimes some channels at the edge have unphysical high value or value with a huge error bar, and it can cause the wrong approximation for separatrix temperature. So we are trying to avoid them, and I know what for this case the good number of channels it is 28. So we add constraints into K files. It will add the separatrix temperature as a constraint, and it will find the 2 points, one on low field side and one on the high field side, and set what they belong to one flux surface, and the temperature should be the same on the both sides. So now we can deselect the profiles and run just the equilibrium. So now we are going to the plotting tab, and we want to see how G files look like if everything looks correct and little. Okay, everything looks fine. When the next quantity what we check the chi-square as function of time. So we can see what's the high Grad-Shafranov error for earlier times and quite good error for later times. We can see the chi-square for magnetic diagnostics and for MSc as well. And the last quantity, what we usually check, it's the error as function of the EFIT iterations. So we can see what error is decreasing for the later times, and maybe it's not the best convergence for the earlier moments. So here we can change some settings and see if we get the better convergence, or if we trust the MSc data, we can increase the weight of the MSc constraints. We also can go to this tab and, for instance, see the chi-square for magnetic diagnostics. And again, if we kind of had a discussion with diagnosticians and we confirm what maybe some probes didn't work properly during the shot, we can change the weight and remove them. We can do the same for MSc channels and so on. Also, we can change the solution relaxation parameter, what can give the better chance to converge. If it has a small value, we also can change the number of maximum iteration. And when we'll get the smaller convergence error at the end. So there are a lot of opportunities to get the high precision of equilibrium. When the user done with this step, we need to add the kinetic constraints to this equilibrium. So we go back to the main tab, we change the iteration to the next one, change it to 1. And we go again to the profile tab. Now we can remap all of the diagnostic data to the new equilibrium, what we got on the previous step. We need to repeat the slicing as we map data to the new equilibrium. While we are doing calculation, I want to show again the OMFIT webpage where we edit the tutorials for our topics. What's been done several years ago for D3D, that contains a lot of useful information. the tutorials for our OMFIT modules, and we have the written tutorials for including the kineticEFITtime. We should find the kineticEFITtime here. And we have a tutorials for specifically for NSTX, where we go through all of these steps and use another discharge as example. So it's a brief explanation how we connect the modules and the philosophy across the different areas where we should use the profiles film and when we run the input code. And we go through all steps as we show during the tutorial. So we finished the slicing. Now we can move to the fitting tab and fit experimental profiles. Here I want to go to the temperature. And first we feed the temperature with radial basis functions. So we can move over times. So maybe with fitting reflects the position of experimental points, but maybe it's not the best choice for the transport analysis. So we can try our fitting methods, but before I want to save this one as radial basis functions. And we can fit this profile with another methods, for instance, the scale length. Usually I decrease the number of knots to get the smooth profiles, what I can use for transp analysis. And usually I also feed the soul to kind of get the better interpolation to the H region, to the soul. So we can fit it again.
You need to press enter.
Right. So now we fitted it with default value, what was -5. Okay, now we can compare the fitting with what we done before. We can see the residual error between the interpolation and experimental points. We can see the comparison of profiles and fitting. And when we can choose which fitting is better according to our philosophy of analysis of experimental data or purpose of the analysis. And yes, to do it with a less number of points. So usually it gives a bit smoother approximation of experimental points. But probably the most suitable if we need to do the power balance analysis and calculate the transport coefficient afterwards. So the different fitting methods depends on the profile shape or the how they want to fit your profiles. Now we will go back to the default settings. We had the radial basis functions, as it's the fastest one and usually works for any type of profiles. And now we will fit all the data with default settings. Next step, we recalculate our post-fit values as we done the new fitting. In outputs, we can see what we calculated. We calculated a lot of derived quantities from our profiles. And one of them, it is that effective, what will be necessary for further transfer analysis. So we had a very raw time resolution. So now we need to update the profiles for the new iteration. I'm doing it here. So we have a new iteration now with profiles, and now we can create our to set up the transplant based on the experimental data. If we do it just by clicking the button, and now it will go through all steps, starting from setting up the input file, when fetching the equilibrium from the equilibrium what we got through EFIT module, when creating U files with experimental values, loading some NSTX specific information about the neutral beams. And at the end, we will see the GUI with opportunity to change any variables in the input name list.
Galina, can you make your OMFIT window bigger? Just maximize it.
Is the transron just to get the fast ion profile?
We get the total pressure from transp, including the contribution from the beam.
So it gives you the current profile.
And yeah, kind of current profile. Yes, we have a.
Okay, so you're really using transp as the input for the pressure profile and.
Yes, we.
Just trying to understand exactly.
Yes, on the first kind of equilibrium reconstruction, we use just the magnetic data and MSC data. And now we analyze the experimental profiles to set up the transplant. And from the transplant, we will get the pressure and current constraints.
Okay.
So we have the input name list with a lot of different variables, what we can change if it's needed. So we can get the help message to understand what this input variable really mean. also can adjust the diffusion for the fast times, what we usually do. Take some time. Usually we use the automatic controller to make the time-dependent fast time diffusion coefficients to match the neutron measurements. So when we are happy with our input name list and our transfer settings, we go back to the main tab. We deselect all unnecessary out tabs, and we submit the transpran. We can see it just here. Calculations will take several hours, and just to demonstrate how we use the pressure and current, we will load the existing run, what I done a couple of days before. But now we can see what's the run being prepared and sent to the transgrid. We can check it on the website, but it's really here, and we will get a message if it's been submitted successfully or not. Here. I didn't pay attention, but it's automatically found the next available run ID and kind of assign it to our transpran. Okay, we can see it here, what it's running, and now we need to wait. So we can cancel this process and transp will continue running, and we just will load the existing transpran. So I know what I've done run with number 40. If the transpran exists, we automatically load the data from NDS Plus server. You can see what the GUI change from setting up new run to kind of analysis the existing run. We have a lot of plots opportunities. We can compare different quantities. But now we will move back to the equilibrium. And now we can see the pressure and current constraints. So we can preview the pressure constraints. So we can see the total current and NBI pressure. So we can set up the BS to H or core. We can change the number of nodes or other settings, like number of points. We can also do the same with the current. First, we preview the current constraints. And usually we change the number of knots and set PS towards the edge, because we trust the current constraints at the core from MSc diagnostics. So we change it here. So now you can see we will use only the width region for the current constraints in equilibrium. Okay, we have pressure and current. Now we can run the new equilibrium.
Maybe, Galina, if you can show the basis functions at some point, or just mention them.
Oh, yeah, sure. I'm afraid we should wait when it finishes. Okay, we have a tab for basis functions, where usually we use autoknot locations. We can see the review. We can see loop over times. So it is possible to change the number of knots. For instance, if we need more to resolve some structures at the edge, we can kind of force them to be on the same locations or on different locations. We also can don't use the autoknot location representation and set it by hands. Sometimes it also might be necessary to use the less number of knots, what we can do only by deselecting with settings. So I can change the number here. And now it should be only 4 points instead of 5, what we had before. We done the kinetic equilibrium. We can go to the plot tab again. We change the iteration number and look on G files. So we can see the some weird values for the Q profile. Probably we need to reduce the number of knots for basis functions for this case. So I think I will go back to the automatic locations, but just reduce the number to 4. And we can restart the equilibrium and see if it gets better. Another option to fix the Q profile, we can set the Q constraints. If we know the value, what should be on the axis, we can just type the value here. And on the next run, it will use this as a constraint. We can go back to the plotting tab, see the G files. Okay, now it looks more reasonable. We can check the arrow or chi-square again. Another metrics what we use to evaluate the equilibrium, they're on the plot tab inside the EFIT module. We can plot the MSE arrow and current. I probably don't want to plot for all of them, maybe just for a couple. So here we compare the EFIT calculations with MSE measurements. We can see kind of good agreement at the center region. The green dots, it is residual between the MSE measurements and EFIT. And we satisfy when it goes through the zero, at least the error bar. And we see not so good agreement at the edge. We can fix it by, again, changing the weight of the constraints. If we trust the MSE measurements at this region, or we should consider our current constraints, what we performed the good transplant, and they have a physical meaning. Or our settings. But at the end, we got our kinetic constraints with pressure and current, what we got from the transplant.
Can I make another comment?
Yeah, sure.
Sorry, I'm making a lot of comments. So this is very powerful. You're able to do a lot of things and see these plots and all this stuff, but it's also very labor intensive. I'm wondering, is this typical of a run for NSTX, for example? You have default settings in all of your, everything that you're showing us, but you often need to check and then end up changing them. Have you been able to find default settings that work most of the time so that you don't have to be changing things a lot? Or is this typical that you often have to check each time slice and change things around?
I would say the settings what we already have here, they are good default settings, what should work for most of the times. The problem, I think, what kind of the time and spatial resolution of diagnostics kind of gives you a lot of freedom and possibility how to fit your profiles, and it will affect your transplant. That's why usually it requires kind of careful check how you do it. But in principle, I would say the settings what we have, they would work for most of the cases.
Yeah, and I, probably if you had to run things automatically, you may want to be more conservative. In general, I think when you run, for automatic runs, you err on the side of robustness versus accuracy. So, I think it depends, and different users have different needs. If you're doing some very expensive gyrokinetic,
I agree with you, absolutely.
It may be worthwhile spending half an hour doing your equilibrium as precise and have as much confidence as possible.
Right. It's sort of two different there's a benefit to each, right? I mean, you know, a lot of people are not going to want to necessarily do this, but some people certainly are. And, you know, there's a benefit to having the automatic runs that get it right pretty much all the time, or maybe most of the time. But you're right. Then you wouldn't necessarily have such freedom on what you choose for everything. So
yeah, so technically you could use this module like Alina showed. You know, you could have all of those boxes checked. You know, run profiles, run transport, run equilibrium. You can actually write a script that will, you know, process a whole run. And in fact, we've done that to create some databases. There is also another module that is called CAKE, which is, I think, it stands for a consistent automated kinetic equilibrium reconstruction. And I think that module has been really tuned for D3D, but there's no reason why it shouldn't be used for NSTX with a bit of work. And the purpose of that one is really like towards being fast and robust, and, you know, just plow through, you know, hundreds of shots. And in fact, there is some work done actually pushed by Egeman at D3D to run that module for all D3D shots. So you know, different tools, different applications.
great, thanks.
If I may add something here, it took me weeks to get the first kinetic EFIT with pipette, and Galina has just shown in an hour that she did like 6 to 10. So I think this is pretty powerful, and I wouldn't think that this was like a slow process. I guess it takes some time to get used to it, but at the end of the day, getting kinetic EFIT for one shot within an hour is pretty fast, in my opinion. Just a comment I wanted to.
Yeah, and also it's multiple time slices, right? So it's not a single time slice.
Yeah, exactly.
Yeah, I don't want to. I apologize if I'm coming. I'm not trying to be antagonistic or critical. I'm just pointing out some differences.
So Galina, was that all you had?
Yes, it was demonstrations, the main features what you can use here.
So I think we'll open up for questions. Other questions if people had any?
I may add a comment that right now we ended at the equilibrium. So we have, you know, if the kinetic equilibrium is really the end point, you know, this is where you would stop. But for example, if you wanted to do some power balance analysis, one thing that you may think of doing is actually go to iteration 2, and then do again the fit of your profiles on a kinetic equilibrium, and then run maybe transp again, but now don't run transp on a magnetics only equilibrium. Now you would be running transp on a kinetic equilibrium, and so now when you do your power balance analysis, or, you know, if you want to do something that for which sources and profiles are really important, you would probably stop at the point 2 of the second iteration.
That's a good point. Any other questions?
I would ask a detail, I suppose. In one of your profile fits, it looked like you had Gaussian plus modified hyperbolic tangents, right? For presumably to try to more accurately fit the pedestal within the way a lot of the analysis has been done. Have you guys tried that with some of the NSTX H modes, you know, inter-elm or something? Like, do you have a sense of the power of using this versus, say, the quote unquote Tom Osborne tools? Or is it effectively that they can be merged through this framework?
I haven't worked with fitting inside the Tom Osborne tools, but I think they both should work in the similar way. There are a lot of settings I think you should adjust for NSTX. I think now it's a kind of the best choice for D3D, but we found what the shape of profiles are different between NSTX and D3D.
Yeah, sure. But it's available for someone to really, like Maddie said, someone's really got to spend real time. Like this takes time to do.
Yes.
Just
As well, there is the option, as she pointed out on Monday, to compare to Tom Osborne's tools if you have a run already there or somebody else does.
mhm.
Yes.
At some point in the very near future, I think I'm going to do that. I have a few profiles from Piped, and I'm planning to do some runs with this kineticEFITtime module. So I think I will do that very soon.
Great.
One question during the EFIT process, the profiles are, well, as far as the profiles are fit with basis functions. So in principle, it would make sense to just use polynomials like spline fits and use those as the basis functions. How is that done within this?
But
Yeah,
it's already
that looks like it. Yeah.
It's already the spline function.
So,
Yeah, but if you fit the profiles with 10H, that kind of needs to be overfit with the splines. So in Piped, as far as I know, first it's fit with 10H, and then that profile is used to do the auto knotting, and then that's how the splines are found or fit. Is this the same process here,
So
or is it
I
somehow
can clear it up. So if you, Galina, if you can click on that interactive preview button.
Mm-hmm.
So essentially what's happening here is that we ran transp, okay? And from transp, we know the P prime and EFIT prime that were, the transp calculated. And so the auto knotting here, what's happening is that basically we're putting the knot. So the blue lines come from transp, okay? And so the auto knotting is basically placing the EFIT knots in such a way that we're giving EFIT the freedom to replicate the P prime and EFIT prime that were calculated by transp. Okay.
I would say,
okay.
yes, I think they're doing the same thing, Maddie.
But there is so there's no assumption about the type of profile fitting that you did during the profile fitting stage. The auto knotting routine is really looking at the P prime and F prime and putting the knots in EFIT such that EFIT has the freedom to match those.
All right. Okay.
So on NSTX, the pedestals are not as sharp as in D3D. But if you were, for example, on D3D, you would see those red points to be more packed towards the edge where there is more structure because of the sharp pedestal.
Okay. Thank you.
Any other questions? Or comments? All right, well, if not,
Maybe just to say that I assume some people will now try and go and do their kinetic EFITs. In fact, we'll probably put this tutorial online so that people can kind of walk through it at their own pace. My suggestion would be to start from the same shot that Galina just showed, and kind of explore, try to wander a bit off the beaten path. Choose different fitting functions and different options. And once people are familiar, with the process, at least once, then they can try their own shot. And I'm sure that there will be problems. That's always how it is. But we have a wonderful team that is happy to work with people and iron out any kind of issues that comes out.
All right, great, thanks. Yeah, appreciate it. Well, if no one else has any other comments or questions, I think we can end it here. I really appreciate it, Galina. I expect people to try this out now and we'll get back to you all. And presumably as people use it, just make never-ending requests for additions and putting new things in, so.
Yeah.
Now, one of the things about OMFIT though is, we do encourage some people to solve their own problems and try and do some of the development.
Please
themselves.
contribute as well.
Yes.
Of course. I know that's a lot of the power is getting, a group of people to contribute. All right, well, I think that's it. We don't have to drag this out any longer, and final call.
Sure. Thank you.
Thank you so much. Really appreciate it, Galina, and the OMFIT group. So thanks a lot.
Thank you, Galina.
Sterling, I'll trust you to stop the recording.